Assalamualaikum and good day again. Okay, so this is a continuation from the first part of the previous video. Okay, just now I mentioned that the last one I mentioned that when we have a high wood ratio or loose soil, so what happened? The voids in the soil skeleton tend to minimize its volume when they have a loading on it, and it lead to a settlement. It lead to a settlement. So I'm not sure that either you knew about settlement or not, but let's me help to explain first. Uh, say so let's say this is initial height of the ground, and somehow we want to build a building on it. So after sometimes the building become significant, the load becomes significant, and what happened is you got a new level of ground. The loading sinks due to the high work ratio. So this part is a settlement. The different height due to the effect of the loading is have a contract, and thus minimize the initial height of the soil. So that's the things that happen due to the work ratio, and also we can relate to the also to the porosity. And here you can see a few example of the range of work ratio value E minimum to E maximum of few different types of soil, but it is not limited to this soil only. As I mentioned before, so for the clay, usually the work ratio is from 0.5 up to 1, but stiff clay got lower work ratio. Soft clay in the middle, it might up to 1.4, but the organic clay can lead until 3.2 of work ratio. So the state of work ratio and porosity is very unique and very variables. It depends to the type of the soil, and it also not similar from the side to another side. Okay, before we go more further, so I would like to highlight again the relationship between work ratio and the porosity. So as we can see from the basic derivation of equation, so volume of voids ratio to the volume of solid, we got the E ratio, and for E it is V sub V to V sub total. V sub V to the V sub total. So means we can relate these two. So we know that V sub Vs is actually V total minus V sub V. So that's why we can have n terms for the work ratio definition. Similarly, we can also derive porosity from the work ratio terms. So in field, if we got only one value, either work ratio or porosity, so we can get the another value because of this relationship. So it means if we need to limit our budget to get a certain measurement only, we only ought to have one type of measurement tools. So it's okay because either one of these can be calculated from either one of the measurement. So that's the benefits of knowing the relationship between work ratio and also the porosity. Okay, next. I would like to introduce the next siblings from my point of view. Okay. So why I'm saying they are also siblings because of the easiness to memorize the equations. So degree of saturation is how much volume of water in the volume of voids, and moisture content, his sibling, also derive about water but compared to the weight of solid, and they use the weight terms and also sometimes the mass term. uh, and note that in this W they use a small letter of W, not a capital letter, but the weight is the capital letter. So, okay, go back to the saturation. So, the first part is water. So, water in voids. This is water compared to solid. So, I hope it is by calling them as a sibling, so you can easily remember them. Okay, a little bit more about the degree of saturation. So, saturation is always important for us as engineer, knowing the how much water is filled up in a soil. So it could be a dry state, 0, and it could be 100% fill up the voids or the state of saturation. Sometimes S also S 100 equal to 100 also can be represented as S equal to 1. So 0 to 1 or 0 to 100. And for water, similarly also expressed as percentage, is also 0 to 100, either in the weight term or mass term. Okay, in the practice, usually we have to do some laboratory testing to define how much the water content, or sometimes also known as moisture content, and small w. This is also small w. Small w. Okay. So what we do is we go to site. We go to a field or site, which will we want to build a building in here. So either you want to build a tunnel or build a building. So just take a small soil sample from the site and bring it to the laboratory, but put it into a container. Of course, there's a lot of process more, as especially when you want to bring the soil. Make sure you keep the lid tightly so the moisture does not um, the moisture can be kept up, and the true moisture is measured when we reach the laboratory. Okay. So the initial weight of the soil with the container is the WW. WW, and the similar soil sample need to be put into the oven from 16 to 18 hours, maximum 24 hours, so that we can dry them. We can dry the soil. So the next day we can measure the dry soil with the container, so we can get the weight of dry, and finally we can do the calculation. So we know that moisture content is weight of water divided by weight of solid. So dry, weight of dry soil minus the weight of container, actually we get the weight of solid. In here, weight of wet soil minus the weight of dry soil, we actually get the weight of wet, weight of water, weight of water. So let's see first example. So moist mass of soil. So here is actually W sub W, weight of wet soil, wet soil, wet soil. And here dry is a weight of dry soil, and here is the container, weight of container. So easily this is a small letter. 20.7 minus 16.3 divided by 16.3 minus 5 kg. So you can get the answer, and we doesn't have any unit anymore, right? So the moisture content either in decimal place, or if you want to get in the percent, you just times with the 100 to get the moisture content in percentage. Okay, so the next one I would like to introduce is about the density in the dry state, of soil. So easily, mass, we doesn't have any mass of air, so that's why ms ratio to the v total, volume of total. So this is in density state. So this is density state. Let's say how to derive for the unit weight of dry. So unit weight of dry, similarly, weight of solids divided by volume total. So we get the weight dry. So this is in kilogram. Oh no, this is in kilonewton. This one, the mass is in kilogram. So density is kilogram per meter. This one. Okay. So now is the next level. We knew that the gamma bar just now is mass total to the volume total, and mass total is actually mass of solid plus mass of water. So and so rho dry, density of dry, we knew ms over here. I could circle that ms, right? So mw, so mw, if we could rearrange the moisture content just now, mw per ms. So we rearrange, we got mw ms times w, moisture content. So we can substitute mw here with the wms, and also ms, of course, this one. So when we can factorize, right? Because we have mass ms, so we can factorize. So the w plus 1 times the ms over the volume total. So remember, ms divided by the volume total is rho d, so we can write like this and rearrange. So when we rearrange, we can get rho d equal to rho divided by moisture content plus 1. And rho, remember, here is also known as a rho bulk, the moist condition of soil moist. Okay, so another things that I would like to introduce is the rho saturated, the saturated density. Okay, saturated density is quite a long equation, so later I will show you. But not to forget, I would like to introduce the submerged density, rho prime, which the effective density of soil when it is submerged. So as example, the soil is already fully saturated, but in the same time, it has flood on it. So that's why we really want to know the effective density of soil only, not including the flood and not including the water and so on. So that's why it comes another equation, rho prime, submerged density. Okay, I think I'll stop here. So later we continue this one and do some derivation in next activity. So thank you and see you again. Bye.